Just about 100 years ago, we didn't know what the surface of Mars and Venus looked like. Today, we've evolved as a technologically advanced species, and there's no longer a need to make guesses. We can not only observe a planet's atmosphere, but even tell what the celestial bodies in our solar system are made of. So is it true that there are oceans of liquid hydrogen on Jupiter? Does it really rain diamonds on Neptune? And are those rings around Saturn really a mile thick? Stay tuned, because you're about to find out about this and more. Scientists have been studying planets for a long time now, and it's not that difficult to get samples of our planet, the Moon, and even Mars. But how do you get information about what a planet's made of that you can't reach? To find out what a celestial body is made of, scientists use many techniques. They combine the information about a planet's density, seismic activity, magnetic field, and so on. But one method is specifically interesting. It's called remote sensing, or spectroscopy, and it involves using light. The process includes using instruments with a grating that spreads out the light from an object by wavelength. The thing is, each element has its own peculiar fingerprint. Scientists then identify this fingerprint in the spectrum of a certain object and can tell what it's made of. So, what have we learned about our solar system so far? As of now, we know for sure what our Sun is made of, including its chemical composition and its internal structure that consists of layers. It all begins at the core of the Sun, or its central part, the place where all the thermonuclear processes happen. The radius of the Sun's core is more than 150,000 kilometers, and it's extremely hot, over 15 million degrees Celsius. By comparison, it's only about 5,500 degrees Celsius on the surface of the Sun. So most of the energy and heat that keeps our solar system warm is generated within that core. But what is it made of? Scientists think that it consists of 64% helium, 35% hydrogen. But if we take the Sun in general, roughly 91% of it is helium. More than 8% is hydrogen, and the remaining elements are pure iron, silicon, oxygen and nitrogen, sulfur and magnesium, and some others. The core of the Sun is surrounded by the radiative zone. It's called this because of the way in which the energy of the Sun radiates to its surface. This region starts about 25% of the distance to the surface and stretches up to approximately 70% into the depth of the star. This is surrounded by the convection zone, or the last layer of the solar interior. This thick layer of the Sun is about 200,000 kilometers deep. Its main function is to transport energy to the surface of the Sun. Hot plasma inside this region churns vigorously, similar to hot lava from a volcano. When it finally reaches the surface, it gives off heat, cools down, and goes back to the bottom of the convection zone. But that's just the internal structure of the Sun. Our yellow dwarf also has a solar atmosphere and outer layers: the photosphere, chromosphere, transition region, and corona. The photosphere is the visible part of the Sun, and it's about 200 kilometers thick. It's this layer that sends the Sun's rays into space. Looking deeper, you'll find the chromosphere, which is much larger, up to 2,000 kilometers thick. In the chromosphere, there's a constant movement of gases. This is where filaments, which are large regions of very dense, cool gas, held in place by magnetic fields, can leap off the surface of the Sun. Sometimes these filaments travel beyond the surface of the Sun up to 250,000 kilometers, and sometimes even overcome solar gravity and break off into space. The next layer is just a few tens of kilometers thick, called the transition region. This is where our Sun becomes very hot. The last outermost part of our star's atmosphere is the corona. From Earth, this layer looks like a radiant halo surrounding the solar disk. The gas here is heated to more than 1 million degrees Celsius. At this temperature, the most common chemical elements, hydrogen and helium, are completely ionized. In other words, they lose all their electrons and stop producing spectral lines of radiation. And therefore, in the visible range of the spectrum of the solar corona, completely different elements begin to dominate, such as highly ionized atoms of iron and calcium. Not so long ago, NASA's Parker probe entered our Sun's outer layer, becoming the first human spacecraft to touch the Sun. If you want to see a video of how it managed to do this and not melt, tell us in the comments. Mercury. Let's move to the closest planet to the Sun, Mercury. At the center of the planet is a core of liquid iron and nickel. The core of Mercury makes up roughly 85% of the planet's radius. However, unlike the Earth's core, Mercury doesn't create a powerful magnetic field. Mercury's magnetic field at the surface is only 1% of the Earth's. Around the core of Mercury is a rocky layer called the mantle. This is approximately 400 kilometers of rock, which mainly consists of silicates. The mantle is surrounded by its thin outer layer of crust. Astronomers believe that Mercury's crust is just about 26 kilometers thick. One interesting fact about Mercury is that it's the fastest planet in our solar system, traveling at about 47 kilometers per second. That's because the closer a planet is to a star, the faster it will travel. Venus. Next up is the planet Venus. The study of the surface of Venus became possible with the development of advanced radar techniques. The most detailed map of the surface of Venus was made by the American spacecraft Magellan, which photographed 98% of the planet's surface. According to one theory, the structure of Venus consists of 3 layers. In the middle lies an iron core, the mass of which is about a quarter of the entire planet's mass. Since the planet doesn't have its own magnetic field, it follows that there is no movement of charged particles in the iron core. Thus, there is nothing that would cause a magnetic field. And because there's no movement of matter in the core, it should have a solid state. Then there's a mantle, which extends to a depth of about 3,300 kilometers and consists of silicate rocks. Above it is the third layer, a crust about 50 kilometers thick, which also consists of silicate rocks. Earth. Up next is the third rock from the Sun. The structure of Earth has been studied for decades. In the heart of Earth, there is a core. Its radius is about 3,500 kilometers. The inner core is solid and is made of iron. The outer core, however, is liquid and consists of a mix of nickel and iron. Interestingly, the inner core rotates at a different speed than our planet, called superrotation. The next layer is the mantle. Its thickness is about 2,900 kilometers. The mantle makes up an astonishing 84% of our planet's total volume. This layer consists of silicate rocks heated to roughly 1,000 degrees Celsius near the crust and up to 3,700 degrees Celsius at its depth. Whenever this red-hot substance bursts upward, volcanic eruptions occur. The third and last layer is the crust, the outer layer of our planet. Its depth extends for 5 to 70 kilometers. The thickest layer of the crust can be found on the continents, while the thinnest ones are at the bottom of the oceans. Mars. Moving farther away from the Sun, you'll find the red planet, which has attracted the attention of scientists since ancient times. Not so long ago, scientists were able to collect precise data about the planet's structure thanks to the probe InSight. The probe measured about 733 Mars quakes and used the information from 35 of them to form a picture of the Martian crust, mantle, and core. Scientists discovered that Mars consists of 3 layers. The deepest is the core. It occupies about half the radius of Mars, about 1,800 kilometers. The total radius of Mars is roughly 3,400 kilometers. Research data shows that the core is liquid, although its large size indicates that it's less dense than previously thought. This means that the core likely contains lighter elements such as sulfur, oxygen, carbon, and hydrogen, in addition to iron and nickel. The next layer of Mars is the mantle. It has an upper, middle, and possibly lower part. The mantle of Mars consists of a single layer of rock with a solid lithosphere extending for 700 to 800 kilometers. To compare, the Earth's lithosphere is only about 100 kilometers thick. However, both lithospheres likely have a lower region where material begins to melt and move slowly. The existence of the lower mantle has not been reliably established yet. Similar to our planet, the outer layer of Mars is the crust. The thickness of the red planet's crust is 24 to 72 kilometers. It's also approximately 4.4% of the total Mars volume. Surprisingly, the crust also consists of 2 layers. The uppermost layer turned out to be unexpectedly porous, and the crust was thin. This points to a high proportion of radioactive elements in the planet's crust. Jupiter. Let's move on to the largest planet in the solar system, Jupiter. Its dimensions are colossal. The equatorial diameter is roughly 140,000 kilometers. The polar one is somewhat smaller, about 130,000 kilometers. You could fit 1,300 Earths inside Jupiter. But at the same time, the actual mass of Jupiter is only 318 Earth masses. The difference in the volumes and masses of Jupiter and the Earth means they differ in average density and differ in internal structure. Low density indicates that the planet consists mainly of light components, hydrogen and helium. Scientists think that heavy elements in the interior of Jupiter account for about 20 Earth masses, or 6% of the total mass of Jupiter. Probe Galileo showed that the structure of the upper atmosphere of the planet consists of 75% of hydrogen and 24% of helium, and the other components are just 1%. As of now, researchers believe that the planet has a solid metal silicate core. One theory is that the core could be surrounded by a shell of hot water, methane, and ammonia in the gas-liquid state under enormous pressure of about 38 million bar. The very same diameter of the core of Jupiter, together with its shell, is 32,000 kilometers. After the core is a layer of metallic hydrogen. The thickness of this layer is approximately 40,000 kilometers. At enormous pressures and temperatures, the electrons in hydrogen atoms break away from the nuclei. The same happens with metals in which electrons move freely. That's why the layer is called metal. After that comes the lower layer, consisting of hydrogen, helium, and mixes of ammonia, ammonium hydrosulfide, and water, which forms 3 layers of clouds. The lower layer is water ice, and possibly liquid water. Its temperature is approximately minus 130 degrees Celsius. Above that, there are clouds of crystals of ammonium hydrosulfide, and the top one is filled with clouds of icy ammonia. But that's not all. Even higher, there's the middle layer of Jupiter, made of 90% hydrogen and 10% helium. And the last outer layer is made of hydrogen only. This is why scientists see Jupiter as a compact, solid metal silicate core, surrounded by a gas liquid and gaseous hydrogen-helium shell, which can be called the planet's atmosphere. And Jupiter doesn't have a solid surface. Gases transform to liquid state and from liquid to solid state gradually over the gigantic radius of the planet, exceeding 70,000 kilometers. But Jupiter is also famous for one other interesting thing. Because of the extreme pressures and temperatures in its atmosphere, hydrogen gas compresses into a liquid. So the planet has the largest ocean in the entire solar system, but filled with hydrogen instead of water. Saturn. The structure of Saturn is very similar to the structure of its neighbor. However, there are still some differences. At the center of the planet is a massive core of solid and heavy materials, silicates, metals, and possibly ice. The mass of the core is about 17 Earth masses. The core temperature reaches at least 24,000 degrees Celsius. This is hotter than the surface of our star. What's even more interesting is that the energy that Saturn's core radiates into space is 2.5 times the energy that it receives from the Sun. Saturn is the least dense of all the planets in our solar system. Its density is less than that of water. What this means is that if space was filled with water, Saturn would float. On the cosmic scale, the rings of Saturn are very thin, about 1.5 kilometers, and their diameter is approximately 250,000 kilometers. Despite their impressive appearance, there are very few substances in these rings. If they were compressed into one body, they would be no more than 100 kilometers in diameter. The particles of these rings are composed of water ice, which, in its turn, consists of solid rock particles frozen into the ice. Uranus. The next planet after Saturn is Uranus. Similar to its neighbor, this planet also has a solid core, which consists mainly of silicate rocks. However, the core of Uranus is larger than that of Saturn or Jupiter. The temperature in the center of Uranus can reach at least 9,000 degrees Celsius. The core is surrounded by a shell of rocks and ice. Above that, there's a 1,000-kilometer layer of liquid nitrogen, gradually turning into gaseous molecular hydrogen. But some scientists think that Uranus does not have a solid core, and at a distance of about 1/3 of its radius from the center, there's metallic hydrogen. The rotation of this planet creates flows of hydrogen that give rise to an electric current. This is where the planet gets its magnetic field from. Uranus has a faint ring system made up of very dark particles ranging in diameter from micrometers to fractions of a meter. These rings consist mainly of microparticles and a small amount of dust. Neptune. The last planet in the solar system is Neptune. Neptune is the 4th largest planet by diameter and the 3rd largest by mass. Its mass is 17 times greater than that of the Earth, while its diameter is almost 4 times greater than our planet. Neptune's structure is similar to Uranus's. Its core is made of iron, nickel, and silicate rocks. The pressure in the planet's center reaches 7 megabars, which is about 7 million times more than on the surface of the Earth. Above Neptune's core, there's the planet's mantle. The mantle of Neptune is rich in water, ammonia, methane, and other compounds. And although this matter is called icy, it's actually a hot and very dense liquid. The farther you get from the core, the more Neptune's surface develops into a darker and hotter atmosphere. It makes up approximately 5 to 10% of the total mass of the planet. The temperature on Neptune in the upper atmosphere is close to minus 200 degrees Celsius. At first sight, Neptune is quite bland compared to the breathtaking Saturn or mighty Jupiter. But there's something about this planet that makes it stand out. Beneath the outer layer of Neptune hides a constant rain of diamonds. Because of the temperatures and high pressure of the planet, methane molecules break apart and release carbon, which forms into chains. And it is these chains that squeeze together, harden, and form patterns of crystal structure resembling diamonds. And because the outermost layers of the mantle are way cooler than the lower layers, as those diamond stones fall, they start heating up and turn into liquid. Then the entire cycle repeats. We told you about the internal structure of the main objects of the solar system, but what did we miss? Tell us in the comments. And subscribe to the channel to stay updated on exciting videos about space.